Okay, everybody, welcome back. Before we get started today, a couple of announcements. Homework 1 is due today, so tonight. Homework 2 is due a week from today, and then Project 1 is due this Friday. So hopefully that's not a surprise to anybody. Right, so let's recap by talking about what we talked about last time, which was this idea of hill climbing. We were talking about local search. And with local search, the idea was that instead of coming up with a sequence of actions that plans to get to a particular goal condition, now we just care about whether a state satisfies some set of constraints, or we care about the state itself is the solution to our problem. So we want a state that maximizes our objective function. And to get there, this idea of hill climbing is we're just going to start at some random state. We're going to look around. We're going to see if any neighboring states has a higher objective value, and then if it does, we're going to move to that state. We just repeat this until there's no more neighboring states around us to go to, and if no neighbors are better, then we quit. We also talked about some upgrades to this. Simulated annealing lets us sort of make sideways moves or backwards moves, like downhill a little bit, and we can do that with some probability according to a temperature, and this can help us to avoid some local minima, or local maxima, I should say. And then we talked about some other upgrades we could make, like random restarts and parallel search and beam search. And someone asked after class, what's the difference between parallel search and beam search, and why is this all related to random restarts? So I wanted to just take a minute to sort of clean that up a little bit and to explain what the difference is between these ideas. So if we start with none of these ideas, what the search looks like is we start with a random state, and then we just do hill climbing, right? So we look at the neighboring states, but first we see the objective value, right? So at time step t equals 0, we have this state, it's the red state, and it has some objective value that's 8. And our objective function just tells us this. So we look at its successors. Each of those successors also has an objective value. The objective value might be higher, it might be lower. If it's higher, we pick it, and then we move that one into the next round, okay? So whatever the best successor is, this is just sort of pure hill climbing. And so we get to this next state. This is time step 2. We generate its successors, and they might be higher or they might be lower. We check their objective values. And if this is just simple hill climbing, we see, okay, no neighbors have improved, so we can actually terminate our search here, and we're done, right? Now, if we're in the simulated annealing case, we might say, okay, well, you know what, I'm going to tolerate this move that technically goes downhill with some probability, and so maybe we keep going and we push the 8 into the next round and hope that it gets better after that. So that's the simple sort of single-threaded case, or the one trial version of this. And we might say, okay, well, we started with 8, we got to 9, or we got to 8. This is not so great. Maybe if we just, we started this 8 arbitrarily. It's an initial state was randomly generated. What if we just try again, right? So this is the idea of random restarts. We come up with some completely different starting state. It also happens to have objective value 8, so maybe that's not the best example, but we'll get to other initial states in a second. And this is time step 3. So after we finished our first trial of local search, we're going to start another one with a different random state, and that's why it's colored yellow. So the search proceeds the same way. We generate successors. We break ties arbitrarily. We pick the best one. We generate more successors. We pick the best one. And now we have value 10, right? So we did a random restart. We got a higher objective value. This seems like random restarts are helping. Maybe we should just throw more random restarts at it, right? So we could do this again. We could do it a third time. And notice that the time steps are going 0, 1, 2, 3, 4, 5, 6, 7, 8. So that the search progresses kind of along this route, right? So one after the other, serial, we're getting from our first search to our last search. So this is the idea of random restarts. And you might think, okay, well, each of these restarts doesn't really require knowing how the previous restart went, so there's no real reason why these have to be sequential. So we could start over and just do them all in parallel, right? So this is what parallel search does. It says we're going to clear the page. Parallel search is going to be on the left. We'll start with all of those random restarts at the same time. Notice that t equals 0 for all of these states. We have all their objective values, and each one's going to generate successors. We're going to pick the best ones. we're going to break ties accordingly, we're going to propagate that into the next iteration, and all the searches are going to proceed at the same time. So we generate more successors, we propagate those forwards. And so now the search looks like this, right? So we have 4 different searches happening in parallel, and hopefully we can get to an answer faster, right? Because we have multi-threaded computers, and you know, we can run this on large clusters, and maybe this will save us some time. So that's parallel search. You're just running all of the random restarts at the same time. None of these are communicating with each other. Yeah, so if they did communicate with each other, maybe there's some even greater savings that we could find, right? So the idea with beam search is we're going to start the same way as parallel search. We're going to have k different copies of our search. They start from k different initial states. We generate the successors the same way as before. But now, instead of propagating the best one of the successors for each different color, we're going to catch all of the best states that were generated. Doesn't matter what color they were, right? So we move these ones into the next generation, and we actually get rid of the dark blue search, right? We don't continue propagating this forwards because 7 is worse than the top k. So we only keep the top k at each step because that's what's going to allow us to keep the same parallelism at each step. And so then we propagate these states forwards, we generate their successors, and again, we pick the top k. So beam search has a number k associated with it. It's the same k that you would have done parallelism with, but now we're saying keep the top k best performing trials. And so we keep those, and if we rearrange them into the descending order, this is what that looks like. And so here the search kind of looks like this, right? So we stop the red and the blue search early because we see that they're not really panning out. They're not leading to as good of values. And so we kind of have this beam that's like expanding at each iteration, and then we're filtering it and narrowing it so that at the next iteration we have the same number of parallel trials. So that's beam search versus parallel search. Does that distinction kind of make sense to people? I'm seeing some nodding heads. Yes, question. Yeah, so the question is, if you end up getting rid of some nodes that are actually quite good, is there any way of accounting for that? So beam search is going to focus its attention on places where the objective value is the highest, and we're going to throw out the red search and we're going to throw out the blue search because they don't have objective values that are as high as the yellow and the teal. So if it's the case that yellow and teal lead us to some local maximum, but red and dark blue would have led us to a global maximum, then we're just kind of out of luck. So this is just how beam search goes, right? So the idea is you're hedging your bets. You're saying, you know, maybe it's best to focus on where the objective value keeps climbing the fastest. And when that's true, that's a good assumption, and beam search will work great. And when that's not true, you might want to go for something more like parallel search, where you keep your options open for a bit longer. Does that answer the question? Great. Other questions before we move on? Okay, so the idea here is that in every iteration, we start with some population of states. We generate their successors. We make a new generation of by mutating those states in some way, and then we evaluate those states based on some sort of like objective function or fitness function, and decide who gets into the next generation. And so we made this analogy last time to genetic algorithms and evolution. And we said that, you know, really there's sort of a natural move that you can make, whereas instead of just doing this mutation piece, which is what we were doing before, and selection, now we're gonna start to worry about like how we would cross over genes between pairs of states. So this is kind of a funny concept, because what we're talking about is like states in a planning problem, and how do those have genes? Like there has to be some way of converting a state in a planning problem into a representation that is like a sequence of bits, or it could be a sequence of digits, or it could be, you know, some, you know, alphanumeric string or some other sequence that we can encode the states into so that we can then split states and cross them over and recombine them and make sort of novel combinations of states. So for genetic algorithms to work, we have to come up with some sort of DNA sequence for a given state. And how you do this is kind of up to you. This is, could be problem specific. And then once you've done that, you can then use your same objective function as your fitness score. And then the selection probability here is kind of like the simulated annealing selection probability. And then once you've selected which pairs of states that you want to continue into the next generation, what you'll do is you'll actually cross these pairs of states. So here we have these two pairs of states, right? So 327 ... and 247. And so what crossing them over is going to do is it's going to say we're going to take this 327, and that's just going to go directly here. We're going to take this 247, that's going to go here. But then we're going to swap these other two pieces, right? And so the gray part is going to go down, and then the white part's going to go up. And so we're recombining the sort of blueprint for a given state, the genetic code for that state, in order to generate novel states, and then we use those novel states in our next generation. We might even mutate them as well, so we might make random changes to certain digits with some probability. And there's other ways that you can kind of encode more of the sort of biological evolution into this process.
Sorry, do you mind just going a little more in depth on what the selection is?
Yeah, so the selection, you can think of this as like if you have a good objective function value, then you might have a higher selection probability. And if you have a lower objective value, you might have a lower selection probability. And this might be dependent on a temperature like simulated annealing, or might not. Yeah. Thanks for the question. Yes? Is the selection a heuristic? I would say not quite. I would say that the thing that's closer to a heuristic is the fitness function, which is really saying how good is this state versus that state. So the fitness function or the objective function or the in simulated annealing, it was like the energy function. Like all of these things are basically measuring how good is a state. And then the selection is just, if you get a worse state, for example, what's the probability that you're going to pick it anyway, like in simulated annealing? Yeah. All right, so I don't want to spend too much time on genetic algorithms. Just know that they are kind of widely used, and this is often how people will do, like when you're figuring out what should the architecture be for a neural network, sometimes people use genetic algorithms for that. I have an example here. We won't have time for it today, but if you're interested, you can kind of think about what would a genetic algorithm look like on this n-queens problem? How would I cross over states to make other states? Would crossover even make sense here? What would mutation look like? What would a good fitness function be for this kind of problem? So I'll let you kind of work through that on your own. But I want to get to this idea of local search in continuous spaces. So far we've talked about discrete search. We had all these ways that we could do planning. We had all these ways that we could do local search in discrete state spaces. But what about continuous spaces, right? The world is continuous, and we might need to solve continuous problems. Let's go back to our favorite country, Romania, and imagine that we're trying to place airports in Romania so that we can minimize the distance from any city to the closest airport. So where should we put these airports? Again, we have to formulate this as a search problem, so we need a state. What's our state going to be? The state's just going to be the positions of the 3 different airports. So X and Y positions for this airport, airport number 1, airport number 2, airport number 3. All of those will just collect into this bold-faced X variable, and we'll say that that is our state. And we might have, we might keep track of the locations of these cities, and then our objective is to minimize the sum of squared distances from each city to the nearest airport. So if CA is the set of cities that are closest to airport A, then we can write down our objective function. It's just minimize this, right? So for all of the different A's, all the different airports, find all the cities that are closest to that airport and add together their squared distances, and this will just be the objective function we want to minimize. So we could use the same sort of search techniques to solve this problem, and it's not even, it's not even that big of a problem that it's a continuous space, right? Like, what we could do, sort of the easiest option is when you have a continuous state space, you could just discretize it and use any of the algorithms that we've already used. So this would mean like dividing up the state space in X and Y into bins or into a grid. And then, if you're closest to this particular bin, you'll just say that it's that value. This is like rounding the continuous numbers to be integers or something like that. And then depending on the size and the coarseness of this grid, you might get better or worse solutions. So if you have a grid that's only accurate to like 100 kilometers, then your airports are not going to be more than 100 kilometers, or they could be off by 100 kilometers from where they really need to be optimal. But then if you get sort of a more refined grid, you can do a better job. It just means that there's more locations that you would need to check. So there's this trade-off between how fine should your grid be to get good optimal solutions, and how coarse should it be to limit the size of the search. So there's this tension there. We could also just, yep, question?
Yeah, on the previous slide, how do you define the cities closest to the airport? Like, what's that threshold?
Yeah, so for each of these, let's say that we've chosen a particular X location. Then the cities closest to that airport you'd look at this city and you'd calculate the distance to this airport, distance to that airport, distance to this airport, and whichever one is the closest you would kind of collect into this airport, and then you would end up with only these squared distances. Thanks for the question. Right, so we could use discrete search, but there's this tension between how coarse should the grid be and how optimal do we want the solutions to be. We could also try just randomly perturbing these individual states and keep trying to do that until something improves the state, right? So this is like keep generating, random perturbations to the state until one of those seems to do better, and then you walk uphill a little bit. This is called first choice hill climbing, and it will work as long as you don't reach a local optimum. If you reach a local optimum, then no matter what you do, you can't perturb the state to get to some higher value, so it'll have those problems. We could also try simulated annealing. Simulated annealing works for continuous problems too. You just have to come up with a different way to sample the neighbors. You have to come up with a continuous sampling process, but it works exactly the same way. It also means that it's going to have all the same disadvantages as simulated annealing. You're going to have to pick a temperature schedule that makes sense, and maybe you have to pick the right number of random restarts or find some parallelism to do it. Maybe a simpler option is we just compute the gradient of this thing, right? So remember from calculus, the gradient of a function is essentially the slope of the hill that you're on, right? So it's the direction of steepest ascent, and the magnitude of the gradient tells you how steep it is. So we could compute the gradient of this function analytically, and then what do? We could set it to 0 and then try and solve for places where this hill has flattened out and we've reached a peak. So how would that look for this problem? Well, this is what the gradient vector looks like. It's just a bunch of partial derivatives, one for each of the components of our state that we care about, right? So this x1, x1, y1, x2, y2, those are just the positions of our airports. And we want basically to know how does changing each of those values, how does changing the x position of the first airport affect the objective function? And so we're going to take all of these partial derivatives and we're going to apply them to this function, which is the minimum or minimization function, the objective function we want to minimize. And so what does that look like? Well, we can do it for one component. The rest won't fit on the slide, but we could imagine doing this for one component. We get this sort of analytical solution. This is the partial derivative with respect to x1. And then we can set this gradient to 0 for all of those different partial derivatives. And then sometimes we can even solve that equation in closed form. So in this case, we can solve it in closed form, and it's saying that the x1 value, the x position of the first airport, is the average x position of all the cities that are part of that same airport, that are closest to that same airport. So we can solve this in closed form. So is this a local or global minimum of that function f? Think about this for a second. Yeah.
I guess would this be a local minimum? Because like we're not sure, maybe like if there's other cities in the airport where like for example like this C1 is different, so like the other airport side, or the some cities that are closest to this airport is different, and that might be the solution that's better.
Yeah, exactly. So for folks who didn't hear, this is a particular solution that solves kind of like the continuous problem, provided that you know which cities are closest to which airports. So for a given setting of which airports collect which cities, this will be optimal. But if you move the airport closer to a city that wasn't sort of in its range before, now you might include that city in this average process, and you'll get a different C1 here, you'll get a different C2. So this is really a local optimum. Essentially we're solving a continuous optimization problem inside of a discrete optimization problem. The discrete optimization problem is which airports should be associated with which cities. And then within that optimization problem, we have this averaging process to figure out where we're going to place these airports for those given cities so as to minimize the distances. Yeah. Did someone decide which cities go with which airports? Yeah, so C1 is the set of cities that are closest to airport 1. Does that answer the question? Okay. Yeah, so who decided which cities go closest to an airport? We did, but we decided that at the discrete optimization step at the top. So we say, if I was going to put these cities with this airport, here's where I would then have to solve the continuous optimization problem. So it's sort of a two-level optimization. And the nice thing about this is that for this problem, we can at least solve the continuous problem in closed form, but the discrete problem might be a little tricky. For some problems, we might not even be able to solve this gradient of f equals 0 explicitly at all. And so in those cases, as long as we can evaluate what the gradient is, we may not need to be able to compute this solution where gradient equals 0. Instead, what we could do is just evaluate the gradient and then move x in the direction of the negative of that gradient. So the gradient says this is the direction of steepest ascent. So if we go in the negative of that direction and we move some amount proportional to that negative direction, then we will slowly descend this gradient hill, and that's why it's called gradient descent. A huge range of algorithms use this for finding extrema with gradients. And this is how most modern neural networks are optimized. Okay, so to summarize, there's lots of configuration and optimization problems that can be formulated as local search. Lots of general families of algorithms. So we talked about hill climbing, we talked about continuous search, we talked about simulated annealing and other stochastic methods. We talked about local beam search and interaction between multiple searches. And we talked about genetic algorithms where we sort of break and then recombine states and mix them back together. Many machine learning algorithms, and we'll get to some of these later in the course, are local searches. So it's good to know sort of what's going on under the hood there. Okay. So with that, that wraps up our unit on search. And today we're going to be talking mostly about games. And so we'll be talking about Minimax and alpha beta pruning, but really the idea here is what happens when we add another agent to the picture? So today's code is player 2, because player 2 has entered the chat. All right, folks, just about ready? Yeah, so games. We all like games. We've heard of them. We've been thinking about them for a while. Games have been like kind of a core component of the field of artificial intelligence for basically the entire length that of time that the field has existed. Why is that? Because as we're designing these AI systems, we want to know how intelligent they are, and benchmarking them on things that we know humans can do and humans can play, then this allows us to have a human agent on one side whose intelligence we roughly can calibrate. Maybe they take an IQ test or something. And then we have an AI system on the other side, and then we're sort of like measuring the intelligence of one against the other. So this helps us to get a metric for how intelligent these systems are. We talked about in the first lecture how there's many different definitions of intelligence, and maybe this isn't the best one, or maybe this is, it might be appropriate in some situations. But this has long been a way that we've tried to evaluate the intelligence of AI systems. And so across a bunch of different games, we've tried to make our AI systems play those games better and better in the hopes that this would lead to intelligent systems. So starting with checkers, in 1950 we had the first sort of checkers player. This is the first computer program that could play the game. Then in 1959, Arthur Samuel wrote this program that could play against itself, and it started to get better. I believe it got better than Arthur Samuel. So that's kind of fun when you write a program that's better at playing the game than you are. And then it took a while, but eventually in 1995, there was this program called Chinook, which was the first computer to beat the world champion. I have an asterisk here because technically the world champion was Marion Tinsley, and Marion Tinsley won against Chinook in the early 90s, and then in 1995, I think it was actually 94, had to withdraw from the sort of rematch game due to health reasons, and they were tied at the point when he withdrew. So it's unclear whether this computer could have beaten the world champion, but it then went on to beat the sort of second best player. After Tinsley died, it defeated Don Lafferty, and it sort of claimed the sort of world champion spot, even though it never actually beat Tinsley. So unclear, but in 2007, we went on to take that program, Chinook, and then use it to completely solve checkers. So what solving a game means is that if both sides play perfectly, we know who's going to win from the start. And so checkers is now solved, has been since 2007. Along the way, we were also looking at chess. Chess was kind of like, a lot of people were looking at chess. It was kind of like the big one. And from 1960 or so to 1996, we were just gradually improving our chess playing abilities using some of the techniques that we'll talk about in this class. And then in 1997, Deep Blue, which was designed by IBM, defeated the human champion, Garry Kasparov. And actually, I got to see the room where that happened when I had an internship there, and I was sitting in the room right next to the room where Deep Blue defeated Kasparov, so that's kind of fun. I hope I sort of soaked up some of that intelligence. And then so now it's 2024, right? So there's these programs out there. One of them is called Stockfish, and these are like open source chess engines. And these things have ratings that are hundreds higher than even the best in the world, Magnus Carlsen. And if you're not familiar with chess ratings, what this means is essentially that if these two players played each other, Stockfish would beat Magnus Carlsen 97 to 99% of the time, and all of the remaining probability would be a draw. So Magnus Carlsen would basically never win against Stockfish. That's how much better these engines are. So chess is about here. It's not solved yet because the game tree is too big to fit into memory, but for all intents and purposes, humans are never going to win against computers at chess anymore. And then there's Go, right? So Go is an even larger branching factor. It's played on a 19 by 19 grid. That means there's about 300 to 400 moves that you could make at any given turn. And so it wasn't until 1968 that there was a program that could even play legal Go, because there's just so many moves you have to pay attention to. Then from 1968 to 2005, we tried some different techniques. Eventually, we reached sort of like novice level. And then after that, from 2005 to 2014, we added Monte Carlo tree search, which we'll talk about on Thursday. And this got us up to sort of like strong amateur level. And the slides are out of order. In 2016, yes. So this is where the slides used to go. And then in 2016, 2017, AlphaGo defeated the world champions. And so then we had to bump this number up. So now we're at sort of human expert level. But there's now this question of whether we may need to bump that back down again, because in 2022, I think I mentioned this in the first class, there was a human exploit of a neural network that there was like this neural network weakness that allowed humans to defeat the top Go engines. So those exploits have since been patched, so I think that this is probably holding steady, but we don't know if there are other exploits out there waiting to be discovered in these neural networks. But you guys aren't here for chess, checkers, and Go. You're obviously here for Pac-Man, right? So what this class will be telling us is, where does Pac-Man stack up on this list of problems? And some would say that's the most important question. Yeah, so with Pac-Man, this is why we're going to need games, right? Because Pac-Man is not the only agent in Pac-Man's environment. So far, we've been doing these search problems where Pac-Man just has to eat all the dots or navigate to certain locations. But when there's these ghosts that you add to the picture, things get a lot more complicated, right? So now Pac-Man has to worry about, where are these ghosts going to go, and what are they going to do when they get there? So Pac-Man's going to move through the maze, and now Pac-Man has to worry about where these ghosts are going to be, has to sort of manage that additional state information, and think about what would make sense for the ghosts to do, and plan for that as well as what Pac-Man needs to do. So there we go. This is the concept of like an adversarial game. So you have two competing agents who are both trying to win, and only one of them can win. And so we've added a second player to the game, and now the search problem becomes more interesting. There's lots of different types of games. Games are basically any task environment where there's more than one player. And there's lots of different ways that we can customize this. So they could be deterministic, they could be stochastic. A deterministic game is like chess or checkers or tic-tac-toe. You know exactly what's going to happen. Every time you make a move, it's the same. If you play a game like backgammon or like Settlers of Catan, like you roll dice and see what happens, those would be stochastic games. There's also perfect information versus partial information. Is the state fully observable, or do I only get to observe part of the state? And so in a game like poker, there's cards, and players are holding their cards hopefully close to their chest, and then the other players can't see what they have. So you have to think about, well, what is the other player doing? What cards might they have? They're betting a lot, so maybe I think that they have better cards, but they might be bluffing. And there's sort of like this process where you're trying to figure out what the other player might be thinking and what cards they might have. So this is an imperfect information game. And then there's the question of how many players are there. Could be 2, could be 3, could be more. Are they in teams, or are they are they acting as individuals? Are they taking turns, or are they all moving at once? So in rock, paper, scissors, both players are supposed to throw their rock or their paper or their scissors at the same time. And if one of them goes first, then it's pretty easy for the second player to choose which one to pick. There's also this idea of zero-sum games where my outcome is the reverse of your outcome. I win the game, or you win the game, or we draw. There's no way for us to both win the game. And so most classic games like chess and checkers have this property. But there's also general-sum games. And essentially what we want is an algorithm for calculating a strategy, which is essentially a mapping from all the possible states we might find ourselves in to the action that we would like to choose in those states. Before, the solution to a planning problem, it could be a sequence of actions, and that worked for deterministic problems, and it worked when there was no adversary, but now there's going to be another agent who's making decisions, and if it's a zero-sum game, they're making decisions to try to minimize our utility, right? We're trying to maximize our utility, but our outcomes are the reverse of their outcomes, so if we win the game, they lose the game. So they're also trying to win, and they're going to take actions to try and make that happen. And so a strategy or a policy is basically saying, well, no matter what action they take, it might bring me to this state, in which case I'll take this action, or it might bring me to that state, in which case I'll take that action. I have a response ready to go for any action that they choose. So that's sort of the difference. Instead of a deterministic sequence of actions, or instead of a state like we had in local search, now a solution is a strategy or a policy. which maps states into actions. So we can start with deterministic games. This is probably one of the simplest types. There's many ways to formalize this, but because we are in this AI class, it's all about sort of rational decision making. We want programs that we can run that are going to solve these kinds of games for us. We're going to formalize it somehow, and the way we'll formalize it is kind of similar to before. We'll start with a set of states. There will be some initial state. This works just the same way as any other planning problem. But now we're going to have multiple players. And so each player is going to get a number. Usually players will take turns. For the sake of this section, we'll assume that they're going to take turns. If you want to formalize it a different way, you can do that. That's fine. You can make it so that they're taking turns simultaneously, or one player moves once and then the other player gets to move twice and then the first player moves again. You can do all kinds of things with this. Each player is going to have a set of actions that's available to them, but notice that different from a single agent setup, now the action may depend not just on the state, but it could also depend on which player, right? So different players could have different actions available to them. There's some board games where this is the case, so it's like an asymmetric type of game. Okay, and then we have a transition function. You can think of this as sort of like the successor function from the search unit. The difference here is we've just written it in math, right? So for a given state and an action, we're mapping to a given next state. We also have a terminal test, which tells us when the game is over. This just takes in a state and says, is the game over or is the game still going? Do we get to keep playing? And then we have terminal utilities. So before we had costs, remember the costs from the search, they were associated with each action. Well, now we're going to say when the game's over, that's when we figure out how well we did. Okay? So at the end of the game, someone wins or someone loses, or someone wins really bad, or wins really well, or loses really bad, and like there's some utility associated with the outcome of this game. And that utility could be different for each player. So given a state that we end the game in, and given a player that we care about, there's some real valued utility associated with that, and this terminal utility function is going to tell us what that real value is. So all of the sort of, this could still be implemented as like there are costs along the way, but essentially now we're deferring all of the utility until the end of the game. Does that make sense? Question? Yeah, your utility is just how much do you like the outcome of the game. So you're going to prefer good outcomes to bad outcomes. So if I'm winning the chess game, I like that outcome. I get a +1. If I'm losing the chess game, I don't like that outcome. I get a -1. If it's a draw, maybe I get a 0. In backgammon, you're allowed to use this doubling cube to decide how many games a win is worth. And you can use this doubling cube during the game, and you can decide if the opponent accepts the double, then the game will end and you'll gain 2 games. So if you win after you've doubled, you gain 2 games and they would lose 2 games. So these don't have to be 1 or -1 or 0. It could be some integer value or it could be some real number. Okay, and so a solution is a policy that maps from states to actions. We already talked about that. This could be a lookup table, or this might be some program that you run. But as long as it takes in a state and it outputs an action, it's a valid policy. So that's the formalization. And, oh, yep, question.
So utility is about how you want to maximize.
Yes. Yeah, utility is how much do I like the outcome of the game? And that's the thing. You want to like it, right? So you want to find outcomes that you like the most. Yeah. Yeah, what's up? Yeah, so previously we would have costs associated with each action, right? Each action A might have a cost associated with it, and so we would add up the costs along the way. And now we're saying that the game is just going to do that for us, and it's going to tell us what the total was at the end of the game. So it's just a different way of thinking about it. Okay, so zero-sum games, which we already talked about, essentially the idea is that there's 2 players, they're fighting over the same sort of resource, or they're trying to win the game, but only one of them can win, and they have opposite utility. So if one agent gets a +5 at the end of the game, the other one gets a -5. Or they could both get 0. So this is pure competition. Anything that one agent gains, the other agent must lose. So there's going to be one agent that's maximizing their utility, and from that same agent's perspective, the other agent is essentially minimizing their utility. This is in contrast with general sum games, where you could have cooperation, you could have indifference, you could have competition, there could be shifting alliances between players. A lot of that and more is all possible, because essentially this player is going for green gems and this one's going for orange gems, and this is this big pile of gems and they don't even care about having the same gems. So this one can get plus 20 and this one can get plus 18, and that's totally fine. They don't have to be the negation of each other. So independent utilities. We'll focus on general sum games later. We're going to focus on zero sum games now. But yeah, that's essentially the idea. And this also works for team games, right? So you can have multiple team members that have the same payoff structure. So if player 2 and player 3 have the same payoffs, then they're going to want to cooperate towards getting the same outcomes. Yeah.
So in team games, it would be still a dependent utility.
Yeah, so 2 of the players or more might have the same utilities for the outcomes, yeah. But it's still general sum, so the other player might or might not have the negation of those utilities. Okay, here's the picture that I want everyone to pay attention to. If there's one thing that you take away from this lecture, it's this picture. In order to make good decisions as the blue agent, we obviously need to start thinking about what is the red agent going to do. And if we're being rational, we should be thinking about what's the red agent going to do. But if the red agent is being rational, it's also going to be thinking about what the blue agent's going to do, right? So this whole cascade of thinking about the other agent, thinking about you, thinking about them, continues as deep as you have memory and time to wait for it to go. So this is the picture, right? So we're always thinking about what's the other agent going to do in response to what I'm going to do, in response to what they're going to do, in response to what I'm going to do, et cetera. So stare at this picture and make sure that that really makes sense. This is more complicated than a single agent game. So in a single agent game, we have Pac-Man, we have a dot. Pac-Man can go one of 2 ways in this maze. It can go left or right. Right? And then from each of those places, it can go left or it can go right again. And then this tree might descend sort of further than I have space to draw. This one won't, because it's eaten the only dot, and maybe the game's over at that point, right? So if we're modeling this as a game, we could say that there's a terminal utility associated with this particular state. Maybe we give it value 8. And the lords of Pac-Man have just decided this value for us, okay? So this is just a number. It comes from our utility function. It says that the terminal utility of this particular terminal state is 8. I don't know how we got there. It could be that under the hood it's implemented as costs per action, and then there's a bonus for winning the game, that kind of thing. So maybe the game gives us 10 bonus points for winning, and maybe it costs us 1 along each of these branches in the tree. But it's not important how those numbers are calculated. The lords of Pac-Man have decreed that this state is worth 8 points when you get there. Okay? And maybe there are some other terminal states down at the bottom of these subtrees. These could be like really long subtrees. They could be infinite subtrees. If we get to terminal states, then they will have values associated with them, also decided by this utility function. So we can talk about the value of a particular state, because essentially we want to take actions to maximize the value that we're eventually going to get to. So we want to, like, if this is the highest number we see in this tree, we want to get to this state somehow, and we want to take actions that are going to bring us there. And in order to do that, we need to know which actions are going to lead to which states that have high value. So the value of a state essentially works like this. It's the best achievable outcome or utility from a given state. So this is really easy for terminal states because they're terminal. There's nothing else that can happen. And this utility function already tells us what the value is. So this is known. So the value of this state, because it's terminal, is just 8. So we can just write that down. But for these nodes, we have to sort of do some computation. It's not a hard computation. It's a maximum. We know how to take maxima. So what we're doing is we're saying, well, in order to compute the value of this state, we have to look at its children's values. and then just take the maximum value from all those children. Okay, so maybe the way that works for this particular problem is, we look at these subtrees and somehow we get that the maximum value for the maximum value for this subtree is, trying to get the pen to work. Right, so let's say that the maximum value for that subtree is 6. The maximum value for this subtree is also 6, and the one for this one is 2, right? So then the value of this state would just be the maximum value between 2 and 6, which would be 6. And for this state, the maximum value for its children would be 8. And that's coming from here. And we could propagate this back up. Once we've calculated these values, we can get the value of the starting state, which is just the maximum of its 2 children, which is 8. And so at each place, we would take the action that maximizes the value. And so we take the action from the starting state that leads to the maximum value. We take the action from the next state that leads to the maximum value. And this would constitute sort of an action selection decision. But the thing to keep in your heads is that none of these states have been generated. The only state that's real here is this first state. The rest of this is happening inside of Pac-Man's head. It's trying to figure out which of these actions is going to lead to the best outcome. And then once it knows that this is the best outcome it can achieve, it comes back up to here and says, okay, I'm going to head in this direction. And we can even replan once we get to this state. We could even start a new search from this particular state. Does that make sense? So the only real state is this first state. The rest of this is just imagining. We're thinking about possible futures. Okay? So this is the single agent case. And how do things change when we add player 2? So now we have an adversarial game tree. The first state has a Pac-Man in it, and it has a ghost in it. And these are 2 different agents. They're both going to be making decisions. Pac-Man's trying to maximize Pac-Man's utility, and the ghost is trying to minimize Pac-Man's utility. So what does that look like? Well, first Pac-Man goes. We're going to say that these players make decisions sequentially. They take turns. So Pac-Man goes and generates 2 states by going either left or right. And notice that the 2 states are outlined in red because the ghost is going to go next. So Pac-Man has 2 possible actions at the first time step, and then the ghost has 2 possible actions. And so for each of those states that we generate, the ghost could go left or the ghost could go right. And those states will look like this. And then it will be Pac-Man's turn to go again, right? So we could have subtrees beneath all of these. These might extend a long, long time. So this is what an adversarial game tree would look like. And notice how the color of the different levels alternates because we're taking turns. First Pac-Man goes, then the ghost goes, and then the Pac-Man goes again, etc. So this is an adversarial game tree. And at the bottom, we might have some utilities associated with these outcomes, right? So we might say, the lords of Pac-Man have decided that these are the, outcomes associated with these states down here, and these ones are associated with those states. I'm going to make this smaller so that it fits on the slide. And let's just say that the lords of Pac-Man have decided that we're playing a 2 time step version of Pac-Man, right? It ends after 2 time steps, and these are the associated utilities with each of those concluding states. So now these are terminal states. I don't know why you would want to play Pac-Man for 2 time steps, but let's just say that that's what we're going to play. So these terminal states, we know the value of them, and we want to compute the value of the other states, right? We want to look at these states, and we notice that sometimes these states are under our opponent's control, right? So the difference versus the single-player version is that Pac-Man could decide the action at every level of the tree. Now Pac-Man can only decide the action at the blue levels of the tree, and the ghost is going to decide the actions at the red levels. So when a state is under the opponent's control, it is going to act so as to minimize the value of the successor states. So we can do that here. We can do the same kind of computation as before, but now instead of taking a max at every level, we're sometimes taking mins. So here the minimum for this state is -10. Even though Pac-Man would like it to be 8, Pac-Man might like to get to this state, which has a high utility. we know that the ghost is going to pick whichever one minimizes Pac-Man's utility here, and that's going to be the minus 10. And similarly over here, it's going to be minus 8. So we back these up, we go up one level of the tree, and now what's Pac-Man going to do? Which one of these actions is Pac-Man going to prefer? Pac-Man's going to try to maximize utility, right? So working opposite to the ghost. So Pac-Man's going to try and go for this minus 8, because minus 8 is still bigger than minus 10. And so the value of this starting state, it's under Pac-Man's control, and so the value here is minus 8. So we're maximizing at the Pac-Man nodes, and we're minimizing at the ghost nodes. Yes? Yes, we'll get to that one later. So more than 2 players, we're just gonna pass on that question for now. But yeah, that's also important. Okay, yes, question?
Would it be similar if both agents can move on like the same time step simultaneously?
So yeah, that's going to complicate things for the algorithm that we're going to look at today, but you can definitely formulate games this way. So that's a different alternative formulation where players make decisions at the same time. And you would need that formulation for something like rock, paper, scissors. Yeah, but we're not going to get into that too much today. Okay, other questions? Yeah? This is a zero-sum game, yeah. So these utilities down here are Pac-Man's utilities. And the ghost utilities are the negation of these utilities. So the ghost would get minus 8 if Pac-Man got to this state. The ghost would get plus 10 if Pac-Man got to this state. So when it's a zero-sum game, we'll typically just write the utilities for one player. But when it's a general sum game or it's a multiplayer game, we might write the utilities for each player. Okay, should we look at another game? Who's played this one before? Only a couple people. I find that unbelievable. Okay, so yeah, in Tic-Tac-Toe, this is a really small game that we also can't fit on the slide. It's way too big for the slide because there's 9 different positions, so there's 9 moves you can take in the first round and then 8 moves you can take in the second round and so on, and that's a lot of moves. But we can formulate it the same way. Each state is gonna be a position in this tree, and then at the first round, the blue player is gonna write an X in there, and that results in these states. And then the next time, the red player is gonna put an O in there, and that results in some of these states. So from this particular node, we're gonna get all of these states as a result. And this is gonna continue until we get to, right, so these are all the states that state leads to. And then we're gonna continue until we get down to these terminal states. And the terminal states, we have awarded utilities depending on which player makes 3 in a row, right? So if the X player gets 3 in a row, then player 1 gets a +1, and player 2 gets a -1. Whereas if the O player gets 3 in a row, then player 1 gets a -1, and player 2 gets a +1. And if they draw, if neither player gets 3 in a row, then they each get awarded 0 points. So this is also a zero-sum game. Okay, so we could think about what the utilities would be. What would be the value of each state in this tree? Well, which states do we already know the value of? The ones down here, right? Oops. The pen likes to be deselected. Okay, so these states we already know the value of, right? The ones that are terminal, because the utility function just tells us their value. To get the value at the next layer up, we look to see whether it's a min node or a max node, and then we take the appropriate min or max. And we can propagate these values up through the tree, and we can get like the value of this node by doing this recursively, right? So we figure out what all the children have for values, and then we figure out what this node has. And this node is a max node, so it would be the maximum of its children. So what kind of values could we have throughout this tree? Could we have like a 0.7? What do folks think? Anybody have an idea? What kind of values could we see in this tree? Yeah. Yeah, why could it only be -1, 0, or +1? Why can't it be 0.7?
Because the terminal like outputs are always -1, 0, +1.
Yeah, so if all the terminal outcomes are these three integers, then we take a max or a min. The only way to take a max or min of 0, 1, and -1 is to have an outcome that's one of those elements, right? So -1 or 0 or 1 is going to be the maximum of those kind of things. So if we run mins and maxes, the only possible values that we can see in the middle of this tree are from that set. And maybe this value is 1, or maybe it's 0, or maybe it's -1, depending on, you know, the mins and maxes and how they work out. There are certain states where, like, I think this state, like, the O is going to have to go here, and then the X could go here, and now there's two different ways to win. So maybe this is winning for the X player, so this might be a value of 1. But there's other states, and you could figure out what the values are for all the states. Tic-Tac-Toe is small enough that you can compute the tree completely, and then you can figure out that, does anybody know what the value of the starting state is? Yeah? 1? You think you can always win tic-tac-toe? Yeah, so if both, it depends on the other player. If both players are playing optimally, you can always force a draw. But if the second player is not playing optimally, then it's possible to win. So going first is definitely an advantage if the other player is not playing optimally. But if they are both playing optimally, then technically the value of the starting state is 0. And you can actually compute this by doing this approach. So this algorithm, this approach, is called Minimax. It's a type of adversarial search. It works for deterministic zero-sum games, and variations of it work for other types of games. But tic-tac-toe, chess, checkers, these kind of games, one player maximizes their result, the other player minimizes the first player's result. Okay? And so essentially, we're going to build this tree. It's going to have some terminal states. Those are going to be evaluated using our utility function. And then we can propagate those values back. And at mid nodes, which we're going to draw as these sort of downward-facing triangles, they point downwards because they're minimizing. So the red nodes are going to be minimizing. So we would basically, I think this is going to build. Right, so these are the terminal values. We're going to compute these ones recursively. And then we can fill in at each level the 2 and the 5 for the minimum of the children. And then at the max, we're going to take the maximum of the next layer. Each node is assuming that the other player is playing optimally, right? So we are assuming we have a rational adversary. They're trying to maximize their reward or utility. Yes? Yeah. Yeah, so if you can't calculate all the terminal values, or if the search tree is too deep to get down there, we're going to deal with that. But we're first going to deal with the sort of easy version where you can. Yeah, so how would you implement this? Well, it's actually kind of simple, right? Because it's just mins and maxes. So on the max side, we can initialize the value of the state to be -infinity. And if we come across any successor that's better than -infinity, which is probably any successor at all, then we're just going to replace the value that we have been sort of keeping our running max inside of V, and then we replace that value with the maximum of V and whatever the minimum value is for each of the successors. So this is recursive, and it's going to call this function, which computes the minimum value. And to compute the minimum value, it's the same thing in reverse. We're going to initialize to some really high value, positive infinity, and anytime we see a successor with less value, we're going to store it inside of V, and then we're going to return that, and we'll hand that back to the max function. But each of these computations is going to require calling the max function, right? So it's recursive. Max is calling min, min is calling max, and this is going to bottom out at some point. I actually don't think the bottoming out is written on this slide. But these are calling each other. This is one way that you could implement it. Yes?
So in an overview, basically, like just the objective would be, let's say if I put X on top left, the agent is going to try to predict where I'm putting it on my next move and then get the best
It's going to consider all the places that you could put it. So if you put an X in the top left corner of the tic-tac-toe board, your opponent, who's playing an O, is going to think about all the places that they could place their O, and then they are going to think about, for each of those places, what are all the places that you could respond with your next X, and so on down the tree.
And then once they choose one, does it go all the same thing, goes down to 3 until it gets to the bottom?
Yeah, so they're not going to commit to a particular action until they have basically stopped their search. They've stopped filling this tree with additional states. So this is one implementation where max is computing this max over successors and min is computing the min. Another way that you could do it is you could have this dispatcher function that says, what's the value of a state? Well, if that state is a terminal state, and now we are handling the sort of bottoming out condition, return that state's utility, and this is just coming directly from your utility function, right? So the lords of tic-tac-toe tell you what the state value is. And then if it's not a terminal state, it's either a max or a min state. So for each case, you will call the appropriate subfunction, and so you'll dispatch. So value we'll call max, which we'll call value, which we'll call min, which we'll call max, which we'll call value, max, and then so on, right? So we're sort of ping-ponging between these two. So this is just another way that you could implement it if you prefer that way. Okay. So let's do an example. Let's suppose that this is our search tree. At the top, we have a player who's blue, and we're trying to maximize the blue player's utility. The first successor that we expand has a red node, and so that means we're trying to minimize utility there. And we start by just initializing these two things with sort of like, what do we think the best value is so far, right? So the value at this state, which we're maximizing, is minus infinity, and the value over here is plus infinity. And then as we look at successors of the red node, we're going to say, well, is 3 smaller than positive infinity? It is. So we're going to cross out this value. Now v equals 3. And then we're going to look at the other successors of the red node. We see a 12. Is 12 smaller than 3? Right, because the red node is minimizing. So if 12 is smaller than 3, we'd want to keep it, but it's not. So we don't keep it. We look at the next successor, and we see an 8. So there's nothing else to do here. We now have calculated the value of the red node. And so we can go back up to this blue node, and we say, well, the value of the blue node is minus infinity unless we find a successor that has more value, because the blue node is maximizing. So now that we've seen this red 3, we can say, okay, well, we can do better than minus infinity. We can at least get 3. So the value at the blue node goes up to 3. You can think about this as like depth first search, because this is really all it is. It's just that how we're keeping track of the values of states is the only new piece. So we're going to go into the next successor of the blue state, which is this red state, which is a min node. And this node is also going to get initialized to positive infinity. We're going to look at its successors. The first one is 2. It's minimizing. So we're going to cross out our positive infinity, and we're going to say v equals 2, because that's the minimums that we've seen so far. Then we look at the next successor. It's a 4. We don't have to update, because the minimum of 2 and 4 is 2. And we see a 6, and so we still don't have to update. So now we know that we've looked at all of these successors. We know that this value is correct. And we go back up to the max node, and do we have to change anything? Who thinks yes, we have to change something at the max node now? Okay, who thinks no? Yeah, we don't have to change anything because this is a max node, so it's saying what is the maximum of its successors? And so it's already at 3, which means that there's an action. If we just go this way, we get a utility of 3. So that means that we don't care about going down this middle route, right? Like this is a worse value. It's going to get us 2. So the maximum is still 3 at the max node. We can do this again. We generate one more successor. We initialize its value to positive infinity. We look at its successors. Okay, 14, that's smaller than positive infinity, so now v equals 14. Now we look at the next one. Okay, now v equals 5. We're minimizing. We're still minimizing, v equals 2. And that's the last successor, so now we know v is 2 here. And again, it's the same situation. We don't have to update the max node because the max is 3. Okay? So imagine we're the blue agent. We've just computed the value of the blue state, and we've done it in such a way that we can label each of the red states with their associated value. And what that means is we know which of those actions produces the best value, right? And so now if we're in this state, we're imagining this big game tree, but we're in this blue state, we have computed that the optimal action for the blue agent to take is to go this way towards the +3. Questions? Yeah.
So in the Minimax algorithm, you always have to look at every single node in the tree.
In this version of it, yes. But we're going to get to that in a second if you can't do that. Yeah, other questions on this part so far? It's pretty straightforward. It's just mins and maxes, right? It's not that hard. And we've already done this stuff with search trees, so it kind of makes sense. So it's nice. Like, it assumes that the other player is going to act rationally. And so if we have a player that is perfectly rational and we're playing against them, then we're going to compute these intermediate values. We're always going to know that, like, the minimum here is 10, the minimum here is 9, and the maximum here that we can do is 10. So of course we want to go this way. And so if we're playing against a perfectly rational agent who's really good at tic-tac-toe, they're always going to be taking the actions that minimize our utility. And this whole picture makes sense. What about if they're not perfectly rational? What about if they're this guy? Right? So if this guy is, is making the wrong action selection here, right? If they're doing this, then they're not implementing the minimum correctly, right? They're not behaving rationally. They're not minimizing our utility. And so we might be able to exploit that in some way. And so if we knew that they were going to make that decision, even some fraction of the time, then we could exploit it and we could maybe take this action more often. But the nice thing about Minimax is that if you have this agent and you're playing against the perfectly rational agent, then you know that you're going to get optimal utility. This case we'll deal with a bit more next time when the agent's making potentially random decisions or suboptimal decisions. Just a quick note, because someone asked on 3 players, so what happens if you have a third player? The same situation, you build a game tree like this, but you flip all the triangles around. So instead of max, min, now we're just going to have max, 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 and the color on the node is going to say which score are we maximizing. Now utilities are going to have 3 numbers associated with them, and we're just going to maximize the number that's corresponding to the color, right? So you can think of this as like Pac-Man and 2 different ghosts, right? So the red ghost makes decisions at the red node, trying to maximize the red ghost's utility, which would be the red numbers down here. Then the blue ghost has a turn, and the blue ghost is trying to maximize the blue utilities. I guess for Pac-Man, those would probably be equal to the red utilities, but this is sort of a general version. And then Pac-Man's going to go on the green nodes and maximize the green utilities, and this whole thing works. So if you have 2 agents who are not playing a zero-sum game, you can do it this way. If you have 3 agents, you can do it this way. Essentially, the terminals have utility tuples. Each player maximizes their own component. And this is cool. Like, this gives rise to cooperation and a competition just organically. It emerges from the fact that these agents either have similar utilities or different utilities. So here's an example. Turn the pen off for a second. Here's an example. I think it takes a while to get started, so I'm just going to jump ahead. Where there's 2 ghosts, and they're coordinating with each other. It takes a while because now they're all planning on what to do. But when they get to this place, they diverge and corner Pac-Man, right? So now their ghosts are working together. There's no objective in there that says that the ghosts have to work together. It's just that they have the same utilities, and Pac-Man has opposite utilities. And so what happens is they coordinate spontaneously, because the red ghost is thinking, well, what would the blue ghost maybe do if it was trying to go for Pac-Man? And so once the red ghost moves, the blue ghost is saying, well, what's the red ghost going to do? And so they're like thinking about, once they've each moved and the red ghost commits to going up, the blue ghost says, well, if the red ghost is going up, then I'm going to go down. And so then they can kind of coordinate and catch Pac-Man. Right? So they're doing this picture. They're thinking about what the other agent is going to be doing. And this might be multiple agents, right? We could have green ones in here too. This algorithm, Minimax, works pretty much like depth-first search. So it takes an exhaustive look at the tree. It has to open up every node. It has to do it in essentially the depth-first search order. And this is going to take exponential time, like branching factor raised to the number of moves in the game. That's a lot of time. It's depth-first search, so you only have to store the number of successors on each level. So it's relatively space efficient. But for chess, finding an exact solution means going through the whole tree, which is 35 to the 100, which is larger than I can count to. So the exact solution is completely infeasible. But do we need to explore the whole tree to be good at chess? Well, we know that we are good at chess at this point, and we know that we don't explore the whole tree, so there must be some way to do this. How did we get there? We have to think about resource limitations, right? Because we can't always just afford to like stare into the distance in the distant future and like find the perfect line through the chess game. One way that we can reduce the size of the tree is we get rid of some of the branches, the ones that we don't need. This is called pruning. So if we go back to this example from before where we had the blue state and the red state, essentially we are initializing the value at each of these states to some bound, which is like lower or higher than the numbers that are associated with the successors. So we look at this 3 and we said, all right, well now we know, maybe we, oops. Right, so we initialize this one, which is a minimum node. So we initialize it to positive infinity, and now we see this 3, and we know that the value, even if we don't look at any of the other successors, it has to be less than or equal to 3. Right? So we have essentially a bound. We haven't opened up these sort of nodes yet. We don't know what they contain, but we know that the minimum is no bigger than 3 because we have seen 3 already. So we open up another node, it's a 12. Turns out that's not less than or equal to 3. We open up another node, it's 8. It's not less than or equal to 3. So it ends up being the case that v just equals 3. But we had this nice bound in the meantime, right? So v equals 3, and then that means that at this node, at the top node, we would have initialized this to minus infinity because we're maximizing. And what that really means is that the value of this state is greater than or equal to minus infinity. Now we opened up a successor, we found that the value of this state was 3, and so now we know that the value of this state is greater than or equal to 3. Right? Because we could always just choose that action, this action. So we can think about this in terms of bounds, and what this allows us to do is when we get to this node, we would initialize this the same way. So v is less than or equal to positive infinity. We open up a successor. Okay, we cross that out. We say v is now less than or equal to 2. And now, do we have to open up any more successors? Yeah, so we can think about, like, what are the values down here, right? There's going to be some values, maybe. So what if we see a value of 1 in here? Is that going to change our decision at the blue node? It's not, because 2 is, like we already know the value of this red state is going to be less than or equal to 2, which is less than or equal to a number that we know how to get. If we just go to the left, we get 3. So we're never going to take this action because we know that red is going to try and, extract as much value as possible, and they're only going to leave us with 2 at most. Maybe they're going to leave us with less. Like if there is a 1 in here, Sure, maybe they'll give us 1. If there's a minus 1,000 in here, maybe they'll give us minus 1,000. But we would rather take the 3. So we're always going to want to prefer this path to stuff that's in this box, because we know that this 2 is essentially blocking us from taking that middle route. So we can actually prune the tree. We don't have to look at those paths. We can prune the tree because 2 is less than our lower bound. Our lower bound is 3, and 2 is less than that, so we don't have to keep looking. We can do this again. We can go over to this successor, and on this successor, we're going to initialize the value to be less than or equal to positive infinity. We look at its children. Okay, now the value is less than or equal to 14. Do we have to keep evaluating? Yeah, we do. Why do we have to keep evaluating? Why can't we just stop early? Yeah, what's a value that could be in this zone that would cause us to want to go here? Well, anything bigger than 14, then the minimum is 14, and this is a better path, right? So if 14 is the minimum, we'd want to go this way. So we can't prune it yet. So we open up another node. We say 5. Okay, 5, that's smaller. V is less than or equal to 5. Okay, we go again. We see 2. V is less than or equal to 2. And now can we prune? Well, it's too late. We've expanded all the successors. We couldn't prune 5 because 5 was still bigger than 3. But now we can't prune because there's no more nodes, right? So now we have V equals 2. We see this 2 here, and we can go back up to this node. We're still going to prefer this route. So what you see here is that the order of generating the successors matters. So if you get the low numbers first at a minimum node, then you can prune quicker because you start out as low as you can go. And so as long as you're lower than the node that the max already had, then you can prune and you can sort of go about your day. So the name of this algorithm is called alpha-beta pruning. Alpha and beta are just sort of like running values of what's the worst or the best that you've seen so far. And we'll talk about alpha-beta pruning next class.